Okay, we have for the next topic, okay, we have characterizations of invertible matrices. And we have regarding a given square matrix A. Again, square matrix in the sense we have the number of rows to be the exact same number as what we have for the amount of columns. And we have for a given square matrix A, okay, we have for the invertible matrix theorem, okay, we have this list of statements to either be all true or all false. And for what we have in the case of the invertible matrix theorem, okay, a couple of statements that really stand out. Okay, we have for the asterisk I have here, we have A is going to have n number of pivot positions. Like if you had the number of rows and columns to respectively be at 3, then you would expect 3 pivot positions. And also, okay, sort of tied in, okay, we have another statement that is going to stand out. We have the columns of the square matrix A to form a linearly independent set. Okay, and this is another way of saying that for the given square matrix A, one column is not going to be a scalar multiple of another. And we have just taking what we have among our samples, okay, and determining if whether each given matrix is going to be invertible. Okay, so we have in the case of sample 1, okay, we have a 2 by 2 matrix where we have A to consist of the top row at 2 and 3 for the elements. Bottom row we have with the elements 5 and 7. Okay, so we don't have 3, 7 to be a multiple of 2, 5 or vice versa. And also we're going to have 2 pivot positions. And just going back to what we had looked at most recently in the case of a 2 by 2 square matrix. Okay, again, this is invertible, and we can use our algorithm where we have the reciprocal of the difference of the diagonal products. Okay, so you have like A times D minus B times C. Okay, so you have 1 over 2 times 7 minus 3 times 5. So this will come out to -1. And again, just flipping the upper left and the lower right diagonal position elements and taking the opposite sign of what we have with the other cornered spaces. Okay, so we have 7, -3, -5, and 2, and taking the opposite sign. So it's going to turn out that for the inverse of A, okay, we're going to come out to -7 and 3, 5, and -2. All right, so this is going to be the inverse of what we have for matrix A. Now we have for the next sample, okay, say we have A is equal to another 2 by 2 matrix where we have the top row elements will be at 2 and 5, and the bottom row elements we're going to have at 6 and 15. And if you notice, okay, this is not going to be a matrix that is going to have an inverse. And one reason for this is that we're not going to have linear independence, okay, because 5 and 15 will be direct multiples of 2 and 6. And in fact, 5 and 15 will be scalar multiples of 2 and 6. Okay, so you have 5 halves times the first column is going to come out to 5 and 15. And so we do not have linear independence. And of course, with this particular square matrix, if I took the product of the diagonals, 2 times 15 is 30. Well, guess what? 5 times 6 is also 30. And 30 minus 30 is 0. And divisibility by 0 does not belong in the real number system. Now, if we look into the next item, okay, so we have a 3 by 3 square matrix. Okay, so we have 1, 0, 2, 4, 5, 8, 7, 8, and 14. And okay, we have a little bit of history to repeat. And this particular matrix is not going to have an inverse. Reason being that we have a scalar multiple among the columns. In fact, the last column is going to be twice what we have for the first column. Where we had the last column elements will be twice that of what we have for the first column elements. Okay, and now we have next item. Okay, so we have with A, this particular matrix A. So we have first row we have at 2, 0, 7. Second row we have 0, 1, 5. Last row we have zeros across. Now, for what we have here, okay, we don't have any one matrix to be a scalar multiple of another. Okay, so we have that particular qualifier. Okay, but now again, we have a 3 by 3 matrix, and we need 3 pivot positions. Okay, now we have for the first column, okay, we have 2's in the pivot position. Next column, we have 1 to be in the pivot position. However, in the case of the third column, okay, we have a 0 at the bottom, so we are missing a pivot element. So in this case, A does not have an inverse, again, because there are only 2 pivot positions where 3 are going to be needed. Now, in the case of what we have with our next and last matrix A, okay, we had 2, 0, 7, 0, 1, 5, and this time we had the bottom row instead of zeros across, we have 0, 0, and 1. And for what we have here, okay, we don't have any one matrix to be a multiple of another. And also we have the pivot positions. We have 2 for the first column, 1 for the second column, and we have the 1 at the bottom, okay, for the third column. So there are going to be 3 pivot positions. So this particular matrix A does have an inverse. And if we look at what it is going to be, okay, so setting up what we have here with the augmented matrix, where we have A and the identity linked together. So looking for the inverse, okay, so if I convert this 2 to a 1, I can take 1/2 of the first row, so we have going across, have 1, 0, 7 halves, and then we have converting the identity, okay, where we have the pivot position adjusted. We have 1/2, 0, and 0, and okay, so we have looking at what we have next. Okay, so we have 1, 0, 0, 0, 1, 0. Okay, so no adjustment needs to be made for the second column, but we have with the third column, we have 7 halves, 5, and 1, and I want to convert the 7 halves and the 5 to zeros. So what I can do here is that I can take the first row and deduct 7 halves times the last row elements. And also we have going from 5 to 0, we take the second row and deduct 5 times the third row elements. And upon doing so, it's going to turn out that we have running across, we have 1, 0, 0, 1/2, 0, negative 7 halves. Second row we have 0, 1, 0, 0, 1, negative 5. And we have with the last row 0, 0, 1. And again 0, 0, and 1. And for what we have on the far right, it's going to turn out that for the inverse of this particular matrix, okay, we have for the top row, again, we will have 1/2, 0, negative 7 halves. Middle row we have 0, 1, negative 5, and for the last row we have 0, 0, and 1.